Welcome to the Deep Dive, your shortcut to understanding cutting-edge AI research. Today, we're dissecting Mem0, building production-ready AI agents with scalable long-term memory.
Right, this is the big one. Anyone working with LLMs knows the frustration of them forgetting things, even within the same conversation sometimes.
Exactly. Forget about remembering details across different sessions. That fixed context window is a real bottleneck.
It absolutely is. So this paper from the folks at research at Mem0 AI dives right into that. They introduce Mem0.
Which is basically an architecture to give agents better long-term memory, right?
Yeah.
It dynamically extracts info, consolidates it, retrieves it.
Yeah, smartly. It's not just about storing more, it's about managing that memory efficiently. And then there's Mem0.
The graph-based one?
Captures more complex relationships between pieces of information. The headline, really, is that both Mem0 and Mem0 seem to outperform the current methods.
And crucially, they do it with less computational overhead. Lower cost, better memory.
That's the claim. So if you're building agents and hitting that memory wall, this paper might have some answers.
Okay, so our mission today is to really unpack Mem0 and Mem0. How do they work under the hood? Why are they potentially so significant? Let's break it down.
Sounds good. You know, the core problem is so relatable. The paper even gives that example, figure 1, I think, where the agent forgets the user's dietary restrictions.
Oh yeah, the classic, didn't I already tell you I'm vegetarian? Problem happens all the time.
It really undermines the feeling of a continuous interaction, doesn't it? Just feels like starting over every time.
And just making the context window massive isn't really a scalable solution. It gets expensive fast, and there are limits.
Exactly. It's a brute force approach. What Mem0 proposes is, well, more elegant. It's memory-centric.
So how does it achieve that? You mentioned it's incremental.
Right. Think of it processing things piece by piece as the conversation happens. There are two main phases, extraction and update. It's like a cycle. Figure 2 in the paper lays this out visually.
Okay, extraction first. What triggers it? What goes in?
It kicks in with every new message pair.
Yeah.
So the user's latest message and the agent's response just before it.
Got it. The most recent turn.
Yeah, but it needs context, right? So it pulls in two things. First, a conversation summary.
A summary, is that static?
No, and that's clever. It's retrieved from a database, but there's an asynchronous process running in the background that keeps updating this summary, so it stays fresh without slowing down the main chat.
Okay, dynamic summary. What's the second context source?
Recent messages, just a rolling window of the last few turns. They used, I think, M10 in their experiments, the last 10 messages.
So you get the big picture from the summary and the immediate back and forth from the recent messages.
Precisely. And all of that summary, recent messages, the new message pair gets bundled together.
Into a prompt?
Yep, a big prompt P, they call it. This gets fed to an LLM they use, GPT-4 Mini, actually, which acts as the extraction function, phi.
Interesting choice, the mini model. Probably for speed.
Almost certainly. Speed and cost. The goal here isn't generation. It's identifying the important bits from that new exchange. The output is a set of what they call salient memories, omega.
Salient memories. So the key takeaways from that term, basically.
Yeah, the stuff worth potentially remembering long-term, judged within the context of the whole conversation so far.
Okay, makes sense. So the system extracts these potential memories. Does it just like dump them into the memory bank?
No, that would lead to chaos, right? Redundancy, contradictions. This is where the update phase is critical.
Right, gotta keep the memory clean.
Exactly. So for each candidate salient memory, omega sub I, it first checks what it already knows. It does a semantic search in its memory database.
Semantic search, using vector embeddings.
You got it. Finds the tops as they used, STEM's most semantically similar memories already stored.
Yeah.
Based on meaning, like you said earlier.
Okay, so it finds related memories. Then what?
Then it packages up the new candidate memory and these top similar existing memories and sends them back to the LLM. But this time it uses a function calling interface, a tool call.
Function calling. So the LLM isn't just writing text, it's being asked to make a specific decision.
Exactly. It has to choose one of 4 operations based on comparing the new fact with the existing similar ones.
4 operations. Like what?
ADD, if the memory is totally new. UP-date, if it adds detail or refines an existing memory. Delete, if the new info contradicts an old memory, super important for accuracy. Or NOOP,
right.
No operation. If the memory is already there, or maybe just not significant enough.
Okay, ADD, update, delete, noop. The LLM decides, and the system executes that command on the memory database.
Precisely. It's a really neat way to maintain coherence and avoid just filling the memory with duplicates or outdated stuff. It's proactive curation.
That does sound much smarter than just appending everything. Okay, so that's Mem0. Now let's talk Mem0. The G is for graph.
You guessed it. Mem0 gram builds on Mem0, but represents the memory as a knowledge graph. Figure 3 shows this. Think nodes and edges.
Why a graph? What's the advantage?
Well, conversations often involve entities, people, places, things, and relationships between them. A graph is a really natural way to capture those connections, which can be more complex than just isolated facts.
Okay, so instead of just a list of memories, it's like a web.
Pretty much. The graph G has vertices, V, edges, E, and labels, L. Vertices are the entities, Alice, San Francisco, Project X. Each node has a type, person, city, an embedding vector, and importantly, a timestamp.
Timestamp for temporal reasoning.
Exactly. And the edges represent the relationships. Alice lives in San Francisco, Alice works in Project X. These are triplets. Source node, relationship label, destination node.
Makes sense. How does Mem0 build this graph from conversation text? Is the extraction different?
It is, yeah. It's a bit more involved. A two-stage LLM pipeline. First, an entity extractor.
Finds the nouns, basically. People, places.
Sort of, yeah. People, locations, organizations, concepts, even attributes. It identifies these key building blocks and their types using an LLM.
Okay. Stage 1, find the entities. Stage 2.
Stage 2 is the relationship generator. It takes those entities and figures out how they're connected in the context of the conversation. It derives the triplets, subject, predicate, object that become the graph edges.
Like lives in or prefers.
Exactly. They use prompt engineering here to get the LLM to look for both explicitly stated relationships and ones that are maybe implied.
That sounds powerful. Potentially captures a much richer understanding. How does updating work in this graph world? It seems more complex.
It is. When a new potential relationship triplet comes in, Mem0 calculates embeddings for the source and destination entities. Then it searches the existing graph nodes for semantically similar entities using a threshold T.
To see if Alice already exists, for example.
Right. And based on that search, it might create 2 new nodes for the triplet, or link 1 new node to an existing one, or just use 2 existing nodes if both entities are already known.
What about conflicts? If I say Alice lives in SF and later say Alice moved to London.
Good question. Mem0 has conflict detection, again using an LLM. But interestingly, instead of just deleting the old lives in SF relationship, it often uses an update resolver to mark the older relationship as invalid.
Ah, so it keeps the history. That's crucial for temporal stuff.
Exactly. It understands that states change over time. It doesn't just overwrite, it invalidates.
Okay, and retrieval. How do you ask this graph a question?
It actually uses a dual approach. First is entity-centric. If your query mentions Alice, it finds the Alice node and then explores the graph outwards incoming and outgoing edges to build a relevant subgraph of information about Alice.
Like a little bubble of context around the entity.
Kinda, yeah. The second method is semantic triplet retrieval. It embeds the entire query and compares that embedding against the embeddings of all the relationship triplets in the graph.
Whoa, okay, so it finds whole relationships that match the query's meaning.
It returns triplets above a certain relevance score. This combo lets it handle specific entity questions and broader relational queries. They mentioned using Neo4j for the graph database and still GPT-4 Mini for the LLM parts.
Neo4j, okay. So we've got the architecture down for both. Mem0 with its curated list, Mem0 gram with its structured graph. The big question, do they actually work better? What did the experiments show?
Right, the proof is in the pudding. They used the LOCOMO dataset.
Which is designed for this sort of thing. Long conversations, memory testing.
Exactly. Multi-session dialogues, lots of questions, single hop, multi-hop, temporal, open domain. It's pretty comprehensive. Big data set too, like average 600 dialogues, thousands of tokens each.
Sounds thorough. They skipped the adversarial questions though.
Yeah, apparently the ground truth for those was missing or unreliable, so they focused on the others.
Makes sense. And metrics, how do they measure success?
They used a mix, standard stuff like F1 and BLEU1, but they admitted those aren't great for factual accuracy in chat.
Yeah, BLEU can be high even if the answer is wrong.
Right, so they relied heavily on LLM as a judge, or J, using a powerful LLM, probably like GPT-4, to score the answers on accuracy, relevance, completeness, things like that.
A more qualitative assessment by another AI?
Pretty much. And they ran things 10 times, reported means, and standard deviations, so it seems robust.
Okay, that's quality. What about efficiency? Cost? Speed?
Crucial deployment metrics. They tracked token consumption, big cost driver, and latency, both search latency, just finding the memory,
Yeah.
and total latencies, search plus answer generation.
Because users won't wait 30 seconds for an answer.
Definitely not. And they compared Mem0 and Mem0 against a lot of baselines.
Like what?
Well, existing LOCOMO benchmarks like Memory Bank, Mem-GPT, an open source one called LangMem, a bunch of RAG setups with different chunk sizes and K values.
Burrow being retrieval augmented generation.
Yep. Also, the brute force full context approach. Even OpenAI's own memory feature in ChatGPT, and another memory provider called ZEP.
Wow, okay. They really tried to cover the field, so the results. Drum roll, please.
Well, the results look pretty good for Mem0 and Mem0. Tables 1 and 2 show they set new state-of-the-art scores for the judge metric on most question types.
Nice. Any specific standout?
Yeah, for single-hop questions needing one specific fact, Mem0 actually did best. Even slightly better than Mem0. And way better than the older baselines.
Interesting. Simpler structure might be faster for simple facts.
Could be. For multi-hop questions needing to combine facts, Mem0 also came out on top. Mem0 didn't show specific gains there, which again suggests Mem0 is efficient at integrating different pieces of info.
Okay, what about harder stuff? Open domain, temporal.
Open domain was interesting. ZEP, one of the baselines, just slightly beat Mem0, though Mem0 is close behind too. Maybe ZEP is better at pulling in outside knowledge.
Plausible. And temporal, the time-based questions.
That's where Mem0 really shone. Highest J-score by a decent margin, clear win for the graph structure and those timestamps we talked about.
Validates the design choice for that kind of reasoning.
Yeah, definitely. And OpenAI's memory feature apparently struggled with temporal, likely because it lacks that explicit time tracking.
How did they stack up against standard R?
They consistently beat all the R configurations they tested. It really suggests that just retrieving raw chunks isn't as effective as having this more structured, curated memory.
Okay, and the comparison everyone wants. Full context. Giving the LLM the entire chat history.
Right. Full context did get the highest overall J-score, about 73%. So in terms of pure quality, having everything is still marginally best.
Oh, the latency.
Exactly. The P95 latency, meaning 95% of requests were faster than this, was around 17 seconds for full context, unusable in real time.
Ouch. Yeah.
Whereas Mem0 was about 1.44 seconds P95, and Mem0 around 2.6 seconds. So maybe a tiny dip in the absolute peak quality, but a massive improvement in speed, like over 90% reduction in that tail latency.
That's the crucial trade-off right there. Near top-tier quality at usable speeds.
Absolutely. Figure 4 shows this latency difference clearly. Mem0 is the fastest search. Mem0 adds a bit of overhead for the graph stuff, but still way faster than alternatives.
What about the memory system's own footprint? Token usage.
Mem0 was quite lean, around 7,000 tokens stored per conversation on average. Mem's grain needed more, about 14,000, because the graph representation is inherently richer.
Still seems reasonable compared to feeding potentially hundreds of thousands of tokens into the context window.
For sure. And compare that to ZEP, which apparently used over 600,000 tokens and had operational issues according to the paper. The Mem0 approaches seem much more practical from that perspective.
Okay, so wrapping up the findings. Mem0 is efficient, great for general and multi-hop recall. Mem0 adds overhead but excels at temporal and potentially complex relational reasoning. Both offer huge latency savings over full context with minimal quality loss.
That's a great summary. Significant accuracy gains over older methods, massive speed up compared to brute force context.
Where do they see this going next? Any future work mentioned?
Yeah, a few directions. Optimizing Mem0 WIFE operations further, naturally. Exploring maybe hybrid or hierarchical memory systems, combining the best of both.
Like Memcure for recent stuff, Mem0 for deeper connections?
Potentially. Also, better memory consolidation techniques, how things get summarized or integrated over time.
Yeah.
And applying these ideas beyond just chat, maybe to procedural tasks or multimodal AI.
It really feels like a solid step towards agents that actually learn and remember over the long haul. Changes the game for how we interact with them.
I agree. It moves beyond the limitations of the stateless LLM call and builds persistent, structured knowledge. The balance between that structure and efficiency is key.
Well, this has been super insightful. Thanks for diving deep into Mem0 and Mem0 with us.
My pleasure. It's genuinely interesting work in a really important area.
All right, so for everyone listening, the big takeaway. Mem0 and Mem0 present really compelling, scalable approaches to long-term AI memory. They're efficient, they outperform many existing methods, and they offer a practical path away from just relying on ever larger context windows.
Definitely worth checking out if you're building complex agents.
Absolutely. You can find the paper and the code linked on their site, memory-centric research. Dive in if you want all the details. And to leave you with something to think about. We saw Mem0's efficiency and Mem0's relational strength. Considering these trade-offs between, let's say, natural language memory versus graph memory, what kinds of specific AI applications do you think would benefit most from each approach? Where would you use Mem0, and where would Mem0 be the better fit? That's it for this deep dive. Join us next time as we explore another piece of cutting-edge research. Thanks for tuning in.